Let's dive right into an explainer that is absolutely going to change how you look at the invisible signals bouncing around our planet right now. We all know GPS is woven into our daily lives, but the truth about what this system actually does under the surface and the catastrophic domino effect if it's suddenly stopped, well, it's pretty mind-blowing.
Seriously, imagine waking up tomorrow to find that the entire GPS network, the literal system holding our modern world together, has just gone completely dark. It's not just your Maps app failing to load. Imagine everything on the ground suddenly blinking 12 o'clock, like an old VCR after a power outage. What exactly would fail first?
The biggest twist here is that GPS isn't actually about telling you where you are, it's about telling you exactly when you are. The global positioning system is, in reality, a massive constellation of flying atomic clocks. They sync to coordinated universal time down to the exact nanosecond, and it's this incredible microsecond timing that serves as the invisible heartbeat for our critical infrastructure all over the globe.
To give you an idea of the stakes here, just look at the financial sector. Global finance clears roughly $24 quadrillion a year. That is a massive number. Financial systems are processing up to 1 billion messages a second. Because high-frequency trading moves at warp speed, regulators require extremely precise timestamps to make sure nobody is unfairly trading ahead of the market. So they completely rely on GPS to timestamp these heuristic trading decisions down to the absolute microsecond.
And you know what else? This exact same microsecond timing is literally what keeps our power grids from collapsing. Power grids use these GPS-dependent devices called synchrophasers to perfectly balance power loads and regulate current flow. If a fault happens somewhere on a massive transmission line, they use the microsecond timing of the electromagnetic waves generated by the fault to pinpoint exactly where the break is. That is what prevents massive cascading blackouts.
We actually got a terrifying preview of what happens when this timing fails back in 2016. An upload error by the Air Force caused satellites to broadcast a time that was off by just 13 millionths of a second. 13 millionths! That tiny fraction of a second caused a massive 12-hour ripple effect globally. BBC Digital Radio went out for 2 days, and across parts of North America, police, fire, and EMS radios completely failed. So, the crucial point is understanding what can intentionally take this system down. We're dealing with two main threats here: jamming and spoofing. Jamming is basically a loud radio shout that drowns out the weak satellite signal with noise. The result? A complete loss of service. It's disruptive for sure, but at least you know you've lost the signal. Spoofing, on the other hand, is like a silent whisper feeding you lies. It sends counterfeit signals, tricking your receiver into calculating a totally false position or time. Your system doesn't think it's broken, it's just confidently wrong.
And listen, this isn't just some theoretical military problem anymore. In just the first half of 2024, the aviation industry saw commercial flights encountering spoofing spike by 400%. On the worst days, this peaked at roughly 1,350 incidents in a single day.
When you look at the global map, it clearly reveals the sheer scale of the problem. Severe interference hotspots are clustered right along major flight corridors. Spoofing and jamming have completely shifted from being niche, defense-specific concerns to massive, daily hazards for civilian aviation across the entire globe. And the trend of GPS signal loss? It is aggressively moving upward. By 2025, the rate is expected to hit 59 events per 1,000 flights. As this interference grows, aircraft are basically forced to revert back to manual, less efficient procedures. For the airlines, this translates to incredibly costly delays, extensive rerouting, and a massive increase in fuel burn.
Section 1. The natural threat, space weather, and solar storms.
Moving away from human interference, we also have to talk about nature. Our sun regularly ejects high-energy radiation and electrically charged gases. A direct hit from a massive coronal mass ejection could be absolutely catastrophic. Back in 1859, a solar superstorm known as the Carrington event was so powerful it literally set telegraph stations on fire, which is, definitely not supposed to happen. If an event of that magnitude hit us today, it could easily penetrate our satellites and spark widespread, long-lasting global blackouts.
If that happens, the economic fallout would be absolutely staggering. Consider this. Since GPS was made available for private sector use back in 1983, just 10 private sector industries, including agriculture, finance, and telecommunications have generated a massive $1.4 trillion in economic benefits directly from this technology.
Because we're so incredibly reliant on it, researchers estimate that a total GPS outage would cost the United States economy a minimum of $1 billion a single day. And the timing of the outage matters immensely. If the system went down during critical agricultural planting seasons, that impact could rocket up to $45 billion.
Section 2. The Resilient Future. E-Lauren and Analog Backups.
Now, all hope is not lost here. When the digital world completely fails, mariners can still thrive using pure math and a sextant. This is a beautiful, completely analog brass instrument used to measure exact angles between visible objects. The best part, it doesn't need a single battery, wire, or satellite to pinpoint your location on the ocean.
Here's the brilliant part, how you actually use it to find a position line. This is called the vertical angle method. First, you look straight through the eyepiece at the flat horizon. Then, you adjust the arm to change the internal mirrors, visually bringing an elevated object, like a cliffside lighthouse, downward. You carefully superimpose the top of that lighthouse directly onto the sea horizon, and then just read the resulting angle right off the physical scale.
Alternatively, you can use the horizontal method. For this, you literally just turn the sextant completely on its side to measure the horizontal visual space between two completely distinct landmarks, say two different lighthouses, across a flat plane.
Once you have that angle, you use this elegant little trigonometry formula. 0.5 multiplied by the chart distance between the objects divided by the sine of your sextant angle. That math right there gives you the exact radius of your position circle. If you cross-reference that circle with a simple magnetic compass bearing, you undeniably pinpoint your exact location on the planet.
So, what should you really take away from this explainer? Mostly, it's that GPS is the invisible, highly fragile utility currently running our modern world. Jamming, spoofing, and space weather are all active, growing threats. And while we've built a futuristic society heavily reliant on space-based time, our ultimate resilience and survival still completely hinge on robust terrestrial backups and timeless analog geometric skills.
Because as the experts at the U.S. Geological Survey remind us, a catastrophic disruption isn't really a matter of if, it's a matter of when. The sun is currently in an active phase, and our critical systems remain highly vulnerable to both natural and human-made interference.
Which leaves us with one final urgent question to think about. When the global clock inevitably stops, is our modern infrastructure truly prepared to survive the dark? Or are we going to be scrambling to remember how to navigate the world when the screens finally go black? Thanks for joining me on this explainer. Keep exploring, and we'll see you next time.